Hi, welcome to R&AC Academy. My name is Ram Prasad. Let me give a small brief about me. I did my masters in R&AC and then I worked for 25 years with the various organizations involving in product development and technology innovation functions. I had 5 patents filed on my name. Out of my passion, I transitioned into teaching. Presently, I am into coaching GATE and IES aspirants on R&AC subject. I also conduct workshop on R&AC systems, faculty development programs, etc. for the engineering colleges. Recently, I conducted webinars for the members of ISHRE and ASHRE. Coming to this program, I am presenting here with a series of lectures on refrigeration systems for the benefit of the students and professionals. I believe these lectures will be of great help and learning to all of you. This is the 9th lecture in the series of lectures on refrigeration systems. In this lecture, let us discuss about the vapor absorption refrigeration systems. Let me start with a small introduction. As per the class's statement, whenever we are transferring heat from a low temperature body to a high temperature body, we need to supply energy for that to happen. However, there are no restrictions on the type of energy to be supplied. So far, we have been discussing VAR systems which will be producing the refrigeration effect with work energy as input. Let us now look at a heat operated refrigeration system called vapor absorption refrigeration systems. While our lives are so comfortable with VAR systems, why at all we need to look at something else? We all know that work is a high grade energy and heat is a low grade energy. If we are able to produce refrigeration using low grade energy, then it will be cheaper. Apart from that, those industries operating with furnaces will be releasing a lot of waste heat into the atmosphere. If we are able to produce refrigeration by utilizing that waste heat, then it will not only be resulting in savings for the organization, but also reduces the environmental pollution. Hence, VARS is used mostly where large amounts of waste heat is available. Also, VARS is used for solar-based refrigeration systems, and hence it makes more sense to the tropical countries like India. In VAR systems, refrigerant alone will be the working fluid, whereas in VARS, a refrigerant and absorbent pair forms the working fluid. How does it function? We will see that in the next slide. However, there is an important note point here. That is, a minimum difference of 200 degrees is required between normal boiling point of the refrigerant and the absorbent. Boiling point of the refrigerant must be lower than that of the absorbent. The popular vapor absorption refrigeration systems that are available in the market are ammonia-based vapor absorption refrigeration system and lithium bromide-based vapor absorption refrigeration system. Let us look at a very high-level details of these two systems. Let us start with the refrigerant. For ammonia-based systems, the refrigerant is ammonia, while water is the refrigerant for lithium bromide-based system. Water is the absorbent for ammonia-based system, whereas lithium bromide is the absorbent for the lithium bromide-based vapor absorption refrigeration system. If you look at the applications, in lithium bromide-based system, as water is the refrigerant, its usage is limited only to the air conditioning applications. On the other hand, ammonia-based vapor absorption refrigeration systems can be used for low temperature as well as air conditioning applications. I will now be presenting a novel interpretation of Vapor Absorption Refrigeration System. Let me start with the VCR system which we have been discussing so far. We had seen that the condenser rejected heat, the expansion device expanded the refrigerant from high pressure to low pressure, and the evaporator produced the refrigeration effect. But the compressor performs three distinct functions in VCR system. First, the compressor sucks the vapor from the evaporator, and then it increases the pressure and increases the enthalpy of the refrigerant. But in vapor absorption refrigeration system, we are eliminating the compressor. Then, does it mean that we don't need to perform these three tasks? The answer is no. Irrespective of the method we adapt, we must ensure that these three functions are performed or taken care of in order to produce the refrigeration effect. So, in total, we have the following tasks to perform here. The first one, we will be getting refrigerant vapor at pressure PE from the evaporator, and we need something to receive it. Second, we need to supply refrigerant vapor at pressure PC to the condenser. Third, we need to facilitate these three functions which are contributed by the compressor. Let us now look at that. Absorber with absorbent receives the refrigerant vapors from the evaporator. The chemical affinity of the absorbent towards the refrigerant actually pulls the refrigerant vapor from the evaporator. The refrigerant and the absorbent forms a rich mixture in the absorber. We are calling it a rich mixture because it is rich in refrigerant. The rich mixture leaves the absorber at pressure PE. A fluid pump increases the pressure of the rich mixture from pressure PE to pressure PC and then delivers the same into the generator. The generator is also maintained at pressure PC. A heat source is available with generator and it supplies heat energy to heat the rich mixture in the generator. As the boiling point of the refrigerant is lower than that of the absorbent by about 200 degrees centigrade, only refrigerant will start evaporating and will get separated from the mixture in the form of vapor. So, the generator now has refrigerant vapor at pressure PC which can be supplied to the condenser. On the other hand, we are left with lean mixture in the generator. We are calling it lean mixture because it is weak in refrigerant. We now need to send this lean mixture to the absorber. But the lean mixture that is leaving the generator will be at pressure PC and we need to maintain the absorber at pressure PE only. Therefore, we need to expand this lean mixture from pressure PC to PE and then deliver it into the absorber. This completes the cycle. Let us now look at how these three functions are taken care of. The absorber performed the function of sucking the vapors from the evaporator. Fluid pump performed the function of increasing the pressure and the generator performed the function of increasing enthalpy. Let us look at the heat interaction that happens in vapor absorption refrigeration system. We had seen in the previous slide that the generator supplies refrigerant vapors at pressure PC to the condenser. In the condenser, these refrigerant vapors will be rejecting heat QC to the surrounding medium, which happens to be the ambient air at temperature TO, and gets liquefied. The refrigerant liquid at pressure PC leaves the condenser, enters into the expansion device, gets expanded to pressure PE, and then enters into the evaporator. The refrigerant absorbs heat QE from the refrigerated space to be maintained at temperature TE by evaporating itself into vapor. The refrigerant vapor from the evaporator will be received by the absorbent in the absorber and forms the rich mixture. The absorber in this process releases heat of absorption to the surrounding medium, which happens to be the ambient air at temperature TO. Heat source at temperature TG supplies heat QG to the rich mixture in the generator. The fluid pump also receives QP amount of energy to run the pump. However, when compared to the magnitude of QG, the QP will be so less that for all theoretical calculations, QP can be ignored conveniently. Let us now look at the COP computation for Vapor Absorption Refrigeration System. But before that, let me summarize the heat interactions which we were discussing in the previous slide. QG is the heat supplied to the generator at temperature TG. QE is the heat absorbed from the refrigerated space at temperature TE. And QC is the heat rejected at condenser to the ambient air at temperature TO. And QA is the heat rejected at absorber to the ambient air at temperature TO. COP for Vapor Absorption Refrigeration System, it is always output by input. And what is that we are producing here? We are producing refrigeration effect, which is equivalent to QE, because QE is the heat absorbed by the evaporator from the refrigerated space maintained at TE. And how to achieve this refrigeration effect? What are we giving as input? That is QG. So this forms the expression for computing the COP for Vapor Absorption Refrigeration System. As I said in the previous slide, that QP can be ignored for all theoretical calculations. Let us now discuss the maximum COP that could be visualized for Vapor Absorption Refrigeration System. A vapor absorption system can be visualized as a combination of a heat engine and refrigeration system. Let me explain this perspective. A heat engine needs a heat source to supply heat to it. Let the heat source be at temperature TG and let QG be the heat supplied by that heat source to the heat engine. And refrigeration system will be absorbing heat from the refrigerated space. Let QE be the heat absorbed by the refrigeration system to maintain the refrigerated space at temperature T. And both heat engine as well as the refrigeration system needs a medium to reject heat to. Let ambient air at temperature TO be the medium to receive that heat rejected by both heat engine as well as the refrigeration system. Heat engine is rejecting heat QA to the ambient air and refrigeration system is rejecting heat QC to the ambient air. In that process, heat engine produces energy W while refrigeration system consumes energy W. And if you are combining these two, then the energy produced by the heat engine is used to produce the refrigeration effect. This is how we can visualize the vapor absorption refrigeration system producing the refrigeration effect using heat energy as input. And for this system, the maximum COP which could be visualized equal to the maximum efficiency of the heat engine multiplied by the COP of the maximum COP of the refrigeration system. We know that the maximum efficiency for heat engine will be Carnot efficiency only, and in this case it is equal to Tg minus To divided by Tg. And the maximum COP for a refrigeration system is nothing but Carnot COP, and in this case the Carnot COP would be Te divided by To minus Te. Therefore, this is the expression to compute the maximum COP that could be visualized for a vapor absorption refrigeration system. This completes this lecture, and in case you have any questions, doubts, etc., please feel free to write to me. In the next lecture, we will be discussing both the gas refrigeration system and steam jet refrigeration system. See you then. Thank you very much.